Welcome back to Basic Electronics. In this lecture, we will use the complete AC equivalent circuit for the common emitter amplifier to find the amplifier gain. Combining the DC and AC solutions for the amplifier, we will obtain the complete solution and compare it with simulation results. We will then look at the frequency response of the common emitter amplifier in a qualitative manner and explain why the amplifier gain varies with frequency. Okay, let us start. Here is the AC circuit again, and we have added the component values. What we want to do first is to obtain the gain for this amplifier, that is VO divided by Vs. And let's remember that all of these quantities, Vs, VO, VB, etc., are signal quantities. All right. So let's look at VO. What is VO equal to? It is this current going through this parallel combination of RC and RL and causing a voltage drop. So it is GM times VBE times RC parallel RL, but that voltage drop is positive in that direction and our VO is marked the other way, so therefore VO is negative of that quantity. So that is minus GM VBE times RC parallel RL. And what is VBE? VBE is the voltage between the base and the emitter, and in this particular circuit it is the same as Vs because the base is connected there, the emitter is connected there. So VBE is the same as Vs, and therefore VO is minus GM times Vs multiplied by RC parallel RL. We now calculate the voltage gain denoted by A with a subscript V, which stands for voltage. Since we have an input voltage and an output voltage, this A is a ratio of voltages, and that's why the subscript V. And there is a superscript L, which is used because the gain includes the effect of the load resistor RL, as we will see. So what is the voltage gain? It is VO by Vs, and we already have VO here in terms of Vs. So all we need to do is to take Vs on the other side, and then we get this expression for AVL. So that is minus GM times RC parallel RL. And as we can see from this expression, AVL does include the effect of RL here. If we change RL to some other value, this is going to change, and therefore AVL is going to change. Okay, now the next step is to evaluate this transconductance parameter, and as we have seen, it is related to the collector bias current. Since IC is 1.1 milliampere, the DC or bias current, GM is equal to IC by VT, 1.1 milliamps divided by 25.9 millivolts, and that turns out to be 42.5 millisiemens or millimos. And now all we have to do is to substitute that in this expression, and we'll get a number for the gain. So AVL is then minus 42.5 millimos times 3.6K in parallel with 10K, and that turns out to be minus 112.5. There is a significance to this negative sign here, and what it says is that if this Vs is increasing, then VO will decrease. So they are out of phase with each other. Let us now calculate the output voltage for an input voltage of 2 millivolts sin omega t. So this 2 millivolts is the amplitude of the sinusoidal input voltage. VO is AVL times Vs. AVL we already know, minus 112.5 times Vs, which is right here. So that turns out to be minus 225 millivolts times sin omega t. So the input amplitude is 2 millivolts, the output amplitude is 225 millivolts, so definitely much larger than the input voltage. What about the collector current? We are talking about the signal current now. That is Gm times VBE, that is the collector current. We already have Gm 42.5 millimos and Vs is 2 millivolts times sine omega t. So if we evaluate that, this milli times milli is micro, 42.5 times 2 is 85. So 85 times sine omega t, that many microamperes. We can now obtain expressions for the instantaneous currents and voltages. In particular, we are interested in the output voltage or the voltage at the collector, and that would be the DC value plus the AC Vc of t, and Vc capital V sub capital C, the bias value we have already seen earlier for this example is 6 volts, and the signal value we have calculated to be minus 225 millivolts times sine omega t. So that is the total instantaneous voltage at the collector. And if we look at the total instantaneous voltage at this node, we are not going to see the DC part because the capacitor is going to block the DC. That DC voltage is going to appear across the capacitor, and here we are only going to see the signal part, 225 millivolts times sine omega t. What about the total instantaneous collector current? Bias current plus signal current. Bias current, as we have seen earlier, is 1.1 milliamps. The signal current, as we saw in the last slide, is 85 microamps, which is the same as 0.085 milliamps times sine omega t. So if we plot this voltage, the instantaneous collector voltage, we are going to see 6 volts, and around 6 volts we are going to see a variation which has an amplitude of 225 millivolts. Similarly, if we plot the instantaneous collector current, we are going to see 1.1 milliamps as the base level, and around that we are going to see a variation with amplitude 0.085 milliamperes. Let us make a few comments now. The procedure that we have followed, that is treating the DC and AC circuits separately and then adding the results, that procedure can be used only if the small signal approximation is valid. That is, the magnitude of VBE should be small compared to VT. In our example, if you recall the last slide, the amplitude of VBE was the same as the amplitude of Vs, and that was surely much smaller than Vt, and therefore the results we have obtained here are valid. If Vs was made larger, let's say an amplitude of 20 millivolts, which means the amplitude of VBE also would be 20 millivolts in our circuit, then the small signal approximation will not hold, and our procedure of separate DC and AC analysis then is not valid anymore. And in that case, a numerical simulation will be required to obtain the currents and voltages of interest. And in this kind of simulation, what is done is the transistor model is considered, for example, the Ebers-Moll model or a more advanced model like the Gammel-Poon model. And the circuit equations for the entire circuit are then solved simultaneously to obtain the solution. In practice, such a situation with large VBE compared to VT is anyway not prevalent, not very common, and that is because, as we have seen earlier, that will give distortion in the output voltage. So even for a sinusoidal input voltage, the output voltage will not be sinusoidal anymore, and that is certainly a situation which we do not desire. So in practice, generally this small signal approximation will be valid, especially for circuits of this type, and therefore we can use DC and AC analysis separately, like we have done here. There are some amplifiers like the so-called class C amplifier, in which the transistor in fact is not operating in the linear region. It is made to operate in the cutoff and linear region, and in that case all of this cannot be used, because the small signal approximation certainly goes for a toss in that case, and then we require a numerical simulation of the circuit or some other approximate way of analyzing it. We will now look at some simulation results to check whether these waveforms are indeed what we expect them to be. So let's quickly go through these equations. Vc of t should have a DC value of 6 volts, and it should go around that 6 volts with an amplitude of 225 millivolts, which means a peak to peak voltage of 225 times 2, that is 450 millivolts or 0.45 volts. So let's remember that number when we look at the simulation results. We will verify whether that is what we see. The collector current has a DC component of 1.1 milliampere, and its peak to peak variation is 0.085 times 2 or 0.17 milliampere. Here are the simulation results. This graph is the input voltage Vs here, which has an amplitude of 2 millivolts as mentioned here, and we are showing 2 cycles, which means 2 milliseconds, since our frequency is 1 kilohertz. So that is 1 millisecond and that is 2 milliseconds. This time is in seconds, so that is 2 milliseconds. And the input voltage is going from 0 to 0.002, that is 2 millivolts, and then going down to minus 0.002. So it's varying between minus 2 millivolts and plus 2 millivolts. As the input voltage varies, the collector current also varies, that is the collector current, and as we notice, its DC value is something like 1.1 milliamp. The current here is in milliamps, so its DC value is around 1.1 milliamp, and it varies around that. And we expect the amplitude or the peak to peak variation to be 0.17 milliamp, if you remember. So let's check whether that is happening. This is 0.05 milliamp, 1.2 minus 1.15. So we have 0.05, another 0.05, another 0.05. So 0.15 and a little bit. So it does indeed look like 0.17 milliamp as we would expect. And this is the Vc, the collector voltage at that node. And what do we expect that to be? We expect it to be centered around 6 volts, that is the bias value of Vc. And we expect the peak to peak voltage to be 0.45 volts from the last slide. Also, we expect the gain to be negative, that is this voltage divided by this voltage, the signal part is negative, and that means we expect Vc to be out of phase with the input voltage, and that is indeed what we see. This is the input voltage and that is the collector voltage. So definitely they are out of phase. When this increases, that decreases, and so on. Its base value, or the DC value, is indeed 6 volts, very close. And the peak to peak variation here, let's see how much that is. This one division is 0.1 volt. So we have 0.1, 0.1, 0.1, 0.1, and maybe 0.02 or something like that. So it's 0.42 or 0.43, and we expect 0.45. So it's reasonably close. So our calculations are fairly accurate, and a little bit of difference, of course, is expected, because the model used here may not be exactly the same as what we did in our calculations. So that's encouraging. Our calculations seem to work, and that means we can use the methods that we discussed. Now, apart from simulation, if you go to the lab and hook up this circuit, you should definitely expect to see the same results. So you can apply an input voltage of 2 millivolts amplitude and see whether your output voltage does indeed look like this. In the lab, you may not easily be able to apply an input voltage with amplitude 2 millivolts, and you may need to use a potential divider arrangement over here, but that's fairly straightforward, and hope you'll be able to do that. What happens if we increase the input voltage amplitude? Two things. One, the output voltage amplitude, or the collector voltage amplitude, will increase. Second, if the input amplitude is too large, then our small signal approximation may not hold anymore, and that will lead to some distortion in the output voltage, or the voltage at the collector. So let us look at these points now. Here is our original input voltage, amplitude 2 millivolts, and that is our original collector voltage, and that's a sinusoid without any distortion. Here are two more cases. This case corresponds to an input amplitude of 10 millivolts, and this case to 15 millivolts. Now the corresponding collector voltage waveforms are shown here. When the input amplitude is 10 millivolts, we start seeing some distortion. The positive half, that one, is looking now different than the negative half. If we increase the input amplitude to 15 millivolts, then we have this output waveform, and now the distortion is more obvious. This positive half definitely looks broader in a way than the negative half. So these are things that we need to keep in mind when we use an amplifier. We should be aware that there is a limit on the input voltage amplitude, beyond which there may be some distortion in the output voltage. Let us now take a brief look at the frequency response of a common emitter amplifier. An example is shown in this plot. How do we measure the frequency response? Here is what we do. We apply an input voltage with a certain amplitude and a certain frequency. We measure the output voltage. Then we take the ratio of the output amplitude and the input amplitude. and that gives us the gain for that particular frequency. Then we go to the next frequency and so on. And when we have all of these data points, then we plot the gain as a function of frequency, as shown in this example. And we should remember, of course, that the amplitude of the input voltage is always kept sufficiently small so that there is no distortion in the output voltage. Now, as we see in this plot, the gain is not quite constant, but there is a frequency dependence of the gain. It drops when the frequency is low, then it is constant for this particular circuit in some range, and then again when the frequency is high, then the gain drops. Now, where does the frequency dependence come from? It's easy to see. Let's take a resistor. The relationship for a resistor is V equal to I times R, and there is no omega in the relationship. So the frequency dependence surely cannot come from resistors. Similarly, this voltage controlled current source does not have any omega in its relationship. So what does have omega is the capacitor. So all of these capacitors, CB, CPi, CE, etc., present an impedance which depends on the frequency. So the circuit becomes frequency dependent, and therefore the gain becomes frequency dependent. And once we understand this point, then it should be easy to see why in the common emitter amplifier we have this kind of behavior. The capacitances CB, CE and CC are large, in the tens of microfarads range or even larger. And for these capacitances, 1 over omega c, the impedance presented by them is negligibly small. That is, they are like short circuits, except at low frequencies. Now this can be seen in this plot here, where we are plotting the impedance presented by the capacitor as a function of frequency, essentially this 1 over omega c. And because it's a log-log plot, both of these axes are log axis, this quantity looks like a straight line. So as we see, 1 over omega c for this case is very small. This is 1 ohm, this is 100 ohms. So it is 1 ohm or smaller in this frequency range, and it starts becoming appreciable only when frequencies are low, let's say 1 kilohertz or lower. What happens then is the following. For example, let's consider CB. In this range, when the frequency is high enough, CB is like a short circuit, and therefore this Vs appears across the amplifier as such. Now when the frequency is low, for example, if we are in this region, the frequency could be 100 Hertz or 10 Hertz, and the impedance presented by CB may then be in the kilo ohms range. Now that becomes comparable to the impedance that is seen from this port, and now there is a voltage division of Vs between CB and the rest of the circuit, and therefore the circuit sees a smaller voltage than Vs, and because of these reasons there is a drop in the gain at low frequencies. On the other hand, the capacitances Cpi and Cmu, the device capacitances, are small. They are in the picofarad range, and for these 1 over omega c is very large. That is, they are like open circuits except at high frequencies, and we can see that also in this plot here. This is 100 mega ohms, this is 1 mega ohms. So the impedance presented by a capacitance of 1 picofarad is small enough only in this range here, and otherwise it is very high, certainly much higher than the other resistances in the circuit like R1, R2, RE, RC, RL. When the frequency is sufficiently low, that is in this region, the impedance presented by C pi and C mu is very high, let's say 1 meg or even larger, and then these could be considered as open circuits. And then all of this current passes through R pi, and that produces some output voltage at the collector. Now imagine that the frequency has increased, say we are somewhere here, so that means the impedance presented by C pi and C mu has now become smaller, and now this current is going to split into different branches, and that's going to reduce the current through this R pi, causing a reduction in the output voltage. So that is what is happening roughly in this region. In summary, there are three regions in the common emitter amplifier frequency response. There is a mid-band region, this region here. In this region, the large capacitances behave like short circuits, and the small capacitances behave like open circuits. So CB, CC, CE behave like short circuits. C pi and C mu behave like open circuits. And in fact, this is the range that we have considered in our analysis, if we remember. That is what we have considered in deriving the gain expression. Then there is a low frequency region in which the large capacitors, the coupling capacitors and the bypass capacitors, they start presenting a sufficiently large impedance and therefore causing a reduction in the gain. Then there is a high frequency region in which the impedance because of C pi and C mu becomes small enough, and that causes a reduction in the gain in this region. So this is a typical frequency response of an amplifier, and depending on what our signal is, we need to make sure that we are operating in the mid-band region where we expect the gain that the amplifier is designed for. In summary, we have completed gain calculation for the common emitter amplifier. Also, for a given input signal, we worked out the complete solution, that is DC plus AC, and compared it with simulation results. We have taken a qualitative look at the variation of the amplifier gain with frequency and pointed out the factors responsible for this behavior. In the next class, we will look at the general representation of an amplifier. So see you next time.